All right, fellas, we are jumping into concavity. Okay, so I'm going to describe what that is and the second derivative. So let me first talk about concavity. And concavity is like concave, right? You're familiar with the word concave. Concave mirrors have, have a curved surface to it, right? So it has to do with how it's curving. So we have two things. We have concave up, which means it's shaped like this, okay? And then we have concave down, which is shaped like this, okay? Now, there's a point where a graph possibly switches from concave up, so you're kind of drawing it like this in this parabola type shape, and then you switch it, right? There's a point where maybe the graph switches and you go like that, okay? So notice the difference here. This place I'm highlighting in blue would be the concave up, right? And this place I'm highlighting with the green would be concave down, okay? The point where it switches in there is called the inflection point. Okay. Now, the second derivative, which I'll get into in a second, is just the derivative of the first derivative. So you take the first derivative, right? You take the first derivative, and we usually call that like f prime of x. And then you take the derivative of f prime of x, but we don't call it that. We call it the second derivative, like this. Okay? So we're just going to take the derivative twice. Okay? And when you take this derivative twice, you're actually going to get a value which will tell you the concavity at that x value. So it's either going to be positive or it's going to be negative. And where it switches from positive to negative is the inflection point. Okay, so we'll get into that here. So let's just look at this graph, and can we tell where this thing is concave up? So where is the graph generally shaped like this? Okay, you'll see that this general shape, and the tangents are all negative here, right? The tangent lines are negative, right? Then they switch to 0. Then they switch to positive. But this whole time, the graph is concave up, right? The graph is concave up. When you draw it with your pencil, you're kind of curving it in this direction. So you'll notice that that is all concave up until we reach this point right here, right? So where is the graph concave up? It is concave up from all the way on the left, and this is going forever to the left, right? So remember, we use the x's to describe where. When we get a question about where, we're using the x's, right? So where is the graph concave up? So all the way to the left is negative infinity to, so negative infinity to, and then we have an inflection point at x equals 2. Okay. Is there any other place where it's concave up? Well, let's look. It switches to concave down now, right? Switches to concave down from 2, it looks like, to somewhere in here. Now, you possibly want to go all the way to 4, but look at how it's shifted. It shifted somewhere in here, right? Somewhere in here. We're going to estimate to be about at 3.5. So it's concave down from -2 to about 3.5. And it's very tempting to say there's an inflection point at x equals 3, but indeed that is wrong. At x equals 4, I should say. It is not at x equals 4, because by the time you get to 4, you'll notice that you're already switching back, right? You're already switching back to concave up, right? This is concave up. So there's two parts where it's concave up. It's concave up from negative infinity to 2, and then once you get past x equals 3.5, so union 3.5 to infinity. Okay. Now, where does it change between concave up? So those are the inflection points. These are what we call the inflection points, right? And the inflection points are at x equals, sorry, I don't know why I put -2 here. This should be +2, right? It switches at x equals 2 and x equals about 3.5, we're going to estimate. Okay, so those are called the inflection points. The inflection points happen where the second derivative is equal to 0. So remember when we had minimums and maximums, so when we had a minimum or when we had a maximum, the first derivative was equal to 0 at the minimum or the maximum, right? Now the second derivative equal to 0 is where the inflection points are, okay? So we're going to be able to use some algebra here, set the second derivative equal to 0 to find our inflection points, where it changes from concave up to concave down or from concave down to concave up. These are the different notations that you will see for the second derivative, okay? This is slightly complicated looking. You'll see it in some literature and things like that. When you get to calculus next year, maybe your calculus teacher will do it something like that. Remember, dy dx is the first derivative, right? And it's a little strange, but they do it. So really what you're doing is, if you think about it, you're taking the derivative of dy dx, dy dx, and then remember, when you take the derivative, you can write it like this, right? The first derivative. But if you're taking the first derivative of the first derivative, you can see how the d becomes squared, and there's only one y. I don't know why I keep putting y down there. And then over dx squared. So it's the whole dx squared. Anyway, it doesn't really matter that much, just so you know where that comes from. But we usually use y double prime or f double prime of x, and I think I miswrote that. We usually put the double prime inside. Okay, so correct that, rewrite that, f double prime of x. Okay. Okay, that's the basics. I'm going to get into this problem in the Google Meet, but you can try it. Okay, you can try to find the first derivative of this function. After you find the first derivative, find the second derivative and set both of those equal to 0, so you can find the max or min here, right? And if there is an inflection point here, okay, if you set that equal to 0. And I'm going to tell you in the Google Meet what that means. The second derivative actually gives us a value that we know in real life. So this is a real life example, and you're going to see a real life example of how the second derivative is used. Let's go ahead. I'm going to do this one on video for number 2. So as we do in math, a lot of times we start with a general case, or we give you definitions, or we try to give you a real life application. But then it's also important to kind of crank out some calculus on the theoretical end. So let's take this cubic equation. We'll just go through here and figure out what is the first derivative. Now, when we find the first derivative, we're also going to find, in this problem, we want to know where it's greater than 0, where it's less than 0, where it's equal to 0. So remember, those are where it's increasing and decreasing, right? And then when we get to the second derivative, we're going to find the inflection points and where it's concave up and where it's concave down, okay? So let me go ahead and go through one example with this. So let's go ahead and take the derivative. Let's take f prime of x, because we want to know where f prime of x is greater than, less than 0, and equal to 0, right? So we need the first derivative. And when we take the first derivative, the 3 comes in front, multiplied by the negative 1/3, and then the x cubed goes down to x squared. I'm going to go ahead and multiply the 2 there. Okay, remember the derivative of 12x is 12, not 12x. And so this becomes -1. This is negative x squared minus 4 plus 4x plus 12, right? And then where is this equal to 0? Notice the instructions here. We're trying to find where the first derivative equals 0. Remember, that's important because that gives us our critical points where it may be a max or a min, right? Now, this one, I usually do not like to factor with the negative in front. So what you can do is bring everything to the other side and make it x squared plus 4x minus 12, right? And you'll see that this factors as x plus 6, x minus 2, okay? So x is negative 6 and x equals 2. So whereas that answers our question, right? Because we set f prime equal to 0. So these are the values where f prime is equal to 0. Okay. Now, remember we made a table last time. A quick way to make a table is actually just to put it on a number line. Okay. So we know it's equal to 0 at x equals negative 6 and x equals 2. So in between those and outside of those, it's either greater than 0 or less than 0, right? So this is where, these are where f prime is equal to 0, right? At x equals negative 6 and x equals 2. We want to know what's happening outside of negative 6 and 2, okay? But remember, this is my derivative up here. This is my f prime of x, right? So now I want to go ahead and plug in numbers that are outside of my interval. So let's plug in a number like negative 8. What happens at x equals negative 8 in f prime of x? So f prime, let me go over here, f prime of negative 8 would be plugging negative 8 in, be very careful, in up here, negative 8 squared minus 4 times negative 8 plus 12. And this is going to be negative 64 plus 32 plus 12, and you'll see pretty easily that that's going to be negative. So it is negative over here, right? Let's choose an easy number here in the middle. Let's choose x equals 0. So what happens when we plug in f prime of 0? Plug it back in. Negative of 0 squared minus 4 times 0 plus 12. And here we're going to get 0 minus 0 plus 12, and it is positive. And you might guess that over here it's probably going to be negative. So let's go ahead and plug in like 5. Okay, f prime of 5 is negative 5 squared minus 4 times 5 plus 12. And this is negative 25 minus 20 plus 12. And you can see pretty easily that you're going to get a negative there as well. Okay, what does that tell us? Well, we already know where f prime was equal to 0. Now I've got to write out where f prime is less than 0, and I need where f prime is greater than 0. But f prime is less than 0 where these things were negative. So negative infinity to negative 6 union 2 to infinity, right? And in between those, it was greater than 0. So this is really, remember, this is telling us where our tangent line is positive. This is telling us where our tangent line is negative, right? Okay. Now, in the Google Meet, I'm going to go ahead and go through doing f double prime, okay? And we're going to go through the same process as we did for f prime, finding it where it's equal to 0 to find why f double prime equals 0. We just have to take the second derivative. So we're going to take the derivative of the first derivative. See you in the Google Meet.